And hello, oh, where did this come from? Here we're starting off with our higher tier stuff as well. So let's have a little look where we're up to. So this is up to question 8 now on the foundation tier. This is the first question that appears on the higher tier. So this is where there's a bit of an overlap in case you were wondering what it looked like on the higher tier. Right, and we start off with a bit of a doozy because loads of people got this first one wrong. Only about 40% of people are getting it right. Lots of people talking about atomic structure and things like that and electrons. Mendeleev in the 1869 did not have an idea about anything to do with that. So you're far more clever, which is why your answer's wrong, even though there is truth to it. So why did Mendeleev reverse the order of these two? It's not because because that's the order they go in, 127, 128. Look, it's the wrong order. It's saying here, there's tellurium and iodine's there, so he's got Te, then I. He's got 128, then 127. That's backwards. So why would he do that? Okay, but he's put iodine with bromine, chlorine, and fluorine. Why would I do that? All right, because obviously they've got similar reactions. People may be kicking themselves a little bit there for that one. This one too. Ooh, this is difficult. Almost half the people that took this test last year got this wrong, 0, nothing. Okay. Sorry if I'm marking yours wrong, but you probably did it wrong too, or parts of it. So, first mark you're getting is for saying that Mendeleev predicted the properties of the missing elements. He didn't just say that there was some missing. That's not why we're getting the mark here, so don't put your hand up and bug me about it, right? He predicted the properties of them as well, and we had a go at that. We said, right, so if this one's this number and this one's this number, pick a number anywhere in between, and that could be a sensible guess. So we've done that in class, okay? Second bit was after his predictions, the elements were then discovered. So we looked at germanium as an example. We called it ecosilicon. And then that discovered element was very close to Mendeleev's predictions, which sort of backed up what he was saying. That's a third mark. Okay. If nothing else, if everything else was a bit gobbledygook, you could have got a mark for saying something along the lines that all the previous ones didn't work and had to be reshuffled whenever they discovered something new, and Mendeleev's didn't. Okay. Right. Most people got the relative atomic mass correct here. The difference between that and the mass number, which some people put down, is that a mass number is just like the top number, which can be different in, for example, chlorine 35 and 37, whereas its relative atomic mass, what actually appears on the periodic table, is 35.5, which is the mass of the average mass of all its isotopes. Okay. Some of you were getting that wrong, sorry. Question 1.4, in the modern periodic table, elements are arranged in order of their atomic number or proton number. I'm not looking for you saying things about electrons or groups or periods, which people did put down, okay? No, 1.5, okay, it's an astatine molecule. What we're interested here, it's because it says a molecule, not an atom, right? It means that there's more than one of them, that's the first clue. The second thing is we know that they should be diatomic in group 7. So F2, Cl2, Br2, I2, which is why the answer for this one is AT2, capital A, lowercase t, a 2 underneath. How am I supposed to know the state at room temperature? Okay, again, patterns in group 7. We start off with things like fluorine gas, chlorine gas. We get down to bromine, which is one of the only 2 liquids at room temperature on the periodic table, and then below that they're going to be solids. Tricky, I understand, I get that. Most people got one of the marks, but not often got both of the marks, apparently, according to the exam results. 1.6. What you'd see from the reaction. Oh, wasn't this first question just mean because it was asking like stuff that you kind of should know but also didn't put? So we're allowed to say a flame, a white solid form, and the colour of gas disappearing. Okay. Most people were talking about what you might see if you put it in water. So you were talking about fizzing or a lilac flame, which, oh no, I understand. Like, you're actually regurgitating information you should know, but it's not what's going on here. So sodium and chlorine, what would you expect to see? It's quite an energetic reaction. So that's where we're getting the idea about a flame or the colour of the chlorine gas disappearing. So that yellowy green colour disappearing. Okay. When it says allow a white smoke forms, that is not the same as saying fizzing or bubbling. Okay, so yeah, few pupils actually got any credit for this, so don't get too emotional about it. Put your hand down, stop bugging me. This is the hoop we've got to jump through for you to get your GCSE. Right, bit of a kick in the nuts for the first one there, eh? Question 2. All acids produce H+. Most people get that right, sort of 80% territory. The most common incorrect answer is the OH-, and that's understandable because that's the alkali one. So here, what sort of acid would make a chloride? That's hydrochloric acid that we'd have to put on this side. And over on this side, most popular incorrect answer is hydrogen, which about 40% of people put. No, when we have a hydroxide, there's oxygen in there, so that means it's not going to be just hydrogen on its own, it's hydrogen and oxygen together. That's water. Right, 2.3. Take a look at the spell for burette. Okay, now I was pretty lenient as long as you were trying to get the word right for it, but you can't accept biuret because that's a reagent that you use in the food testing. Okay, look at the spelling, practice that. Looking at the reading, it was 27.6. Most commonly incorrect at 28.4, because you're not going 28 and then going up to here, it's going 27, 28, 29, the scale's going down. Don't get caught out by this. Right, 6-mark question on titrations. It's not panic territory because there's no calculation on it. Okay, describe how you could use titrations. A lot of people got a lot of marks for this. Okay, so measure the volume of the acid using, say, like a 25 ml pipette. Add an indicator. It just says an indicator here. I'd love it if you said a suitable one. You could say methyl orange, you could say phenolphthalein, you could even include litmus. Don't start talking about universal indicator. We're looking for something that changes colour once. Okay, so that is describing this stage here, how we get the 25 ml of acid into there. Okay, next step, you'd be talking about filling up your burette with with your sodium hydroxide, and then you'd be adding that slowly until you get a colour change. Okay, you'd need to record your result and repeat it. Once you've done it with both different sources of acids, you could then compare it with the one that uses the most sodium hydroxide to neutralise it being the most concentrated. Okay. Along the way, you need to have talked about something you've done to make sure that you are being accurate. Okay, so for the 25 millilitres of sulfuric acid, you could have mentioned using a pipette and a filler. For the indicator, you could say a few drops. You could be talking about swirling or using a white tile so that you can ensure that it reacts and that you can see any colour change. You might have mentioned doing it as a rough go first time through, or going a drop at a time at some point, or even repeating things and taking a mean. A level 3 answer then is going to be logical, so the steps are going to follow on step by step with the instructions in order. When it says a valid outcome, it's going to explain how you can tell the difference between the two, so that if I followed your instructions, I could actually get the results. And it's also going to have some of those other points included about how to be accurate. Okay. A lot of people, I don't really remember giving many people 6, because I think probably some of these points down here were missing, or it was a little bit of a problem somewhere in the order or structure of what you're writing. Look at this, question 3 already. We're having so much fun. Yeah, stop glaring at me with those eyes. So, explain why carbon nanotubes conduct electricity. When we talk about conducting electricity, we're either talking about ions or electrons. In this case, because it's carbon, just like the graphite, you'll have the same explanation. It's got 3 electrons. There's your first mark, and that's some people's only mark. The second mark is for saying what those electrons can do, so they can carry a charge throughout the through the structure. Okay, you know it says down there ignore throughout, because it will only be along that layer of tube. It won't jump from one tube to another tube. For 3.2, we're looking at this badminton racket question. Generally well done. Okay, now biggest point, don't just copy down the points at the table. Don't say aluminium has 2.7 and has 0.3 and has 6.9. Relate these to the job of it. So density, we want a low density for a lighter racket so that we can move this fast. That's important for badminton. Strength, we want it to be strong. Stiffness, being stiff is good excuse me, for a badminton racket, because if it was bending, then it's it might give it a little bit of an elastic whip to the power, but it's also not going to be where you want it to be when you want it to hit it. Okay, so if you've given some good and bad points about each of those along the way, then you might just have 3 marks, and the 4th mark is it's an evaluation, so you've got to make a choice. So I'd expect people to be saying that the carbon nanotubes are good because they are strong and they are lightweight. The biggest problem for them is that they're not as light as wood. Would be a better choice? No, because it's not very strong at all and it's nowhere near as stiff. Aluminium, some people said, could be a decent choice because it's cheaper, which is fair enough to say. It is the most dense out of them, so it might be like your entry-level budget cheap version rather than your, I'm going to go to the Olympics and actually win sort of racket. Okay. 3.3. Couple of people fail on the basic maths here. Okay, we're looking at the surface area, not the volume. So it's not the length times the width times the height. We're looking at for the area. So this square on top, that would be 82 by 82, which would be 6724 nanometers squared. Now, how many sides does this square have? 1 on top, 1 underneath, 1 in front, 1 behind, 1 on the left, 1 on the right. That's 6. So we times it by 6, and we get 40344. And then we need to put it into standard form. Okay, so we're going to make it 4.0 because that 3 can get rounded down, and then we'd have to move the decimal place 4 places, so 4 times 10 to the 4. Okay, so if you messed up on your calculations up here, you can still get a mark for putting an answer in standard form, even if it's the wrong answer. It's worth going to go for a mark, isn't it? For 3.4, why does it cost less to use nanoparticles? Quite a lot of people, half of them only scoring this mark, so half failing at it. You can't just say nanoparticles are smaller or easier to manufacture or take less energy. The key thing here is when we're doing this, because they're smaller, you need less materials to make it. That's the key thing. So we can use less, or we've got a greater surface area to ratio. Let's have a look at question 4 then. It's about time you had an easy mark, isn't it? Now this is very well answered. Most people were getting stuff on this right. I don't see why this couldn't have been some of this stuff in question 1A. So the relative mass on a neutron is 1 and its charge is 0. That's your first mark. The other particle that we needed to name is a proton and it's got a mass of 1. Okay, so most people got those correct. And I can't see why not. You should know that stuff by now. Defining a mass number, again, people did well. It's the number of protons and neutrons added together. Do take a look here at the mark scheme. If you got it wrong, it says, do not accept references to the mass or relative mass of protons. It's not saying how much they weigh, it's the number of them. Okay. 4.3. Why is the mass number different in isotopes? There's a different number of neutrons. Notice that came up in the foundation paper as well. And 4.4, yeah, quite well answered from our people here. If you lost marks, it was for something that you probably kicked yourself over. Okay, so the key points that I'm looking for you including is that most particles go straight through, and that means that there is mostly empty space, or if there is any mass, it's concentrated in the middle. Okay, don't just say, so there is a nucleus. We actually need to know what that means. Some of the particles were reflected or deflected. So for those, you could either say that either it's a very small mass in the middle which to deflect it off, or the particles were repelled by a positive charge. Okay, let's go on for question 5. So like in the foundation tier, you guys have got to do a dot and cross diagram, but you haven't got any hints or clues on this, but you did pretty well on it overall. So if we look at the diagram over here on the right, we've got a dot and a cross anywhere in these overlaps, just like a Venn diagram. And that would take nitrogen up to 6 electrons in its outer shell. And then obviously there would be 2 more unaccounted for. So anywhere in the nitrogen area not overlapping with the hydrogen, you put the other 2 dots. That's what most people did. Most people did that. Okay, not much more to say about that. The limitation though, okay, very small proportion of people naturally were able to do this. You did give some common sense limitations, but we're actually talking in the vein of where we are at the moment, like using it in chemistry. So the biggest thing is it's only two-dimensional. It doesn't show it as a 3D shape. Okay. For 5.3, why has ammonia got a low boiling point? A lot of 2 out of 3 marks on this because you've not mentioned the type of bonding. Okay, so a lot of people found this difficult. So the first mark could be for saying it's a simple covalent structure, or if you said small molecules. The second mark is for saying there are weak intermolecular forces holding the molecules together. All right, the bonds holding the nitrogens and hydrogens have got nothing to do with this answer. Notice it's allowing weak intermolecular bonds there, but it's not exactly what we're looking for. The third mark is for the classic line, little energy is needed to overcome these weak intermolecular forces. 5.4, hey, we're motoring, we're getting there. 2, 3, maybe people got this right. People found this difficult, and again, this came up in the foundation tier, right? Transition metals are good at being catalysts. Your question is just a little bit more difficult because it's more difficult to spot the transition metal in there. It's chromium, okay? That's why you're selecting chromium. It's in our transition metal block. On question 5.5, you need these bond energies to work out the overall energy change. Okay, most people did really good on this, so I'm not going to spend too long talking about it, but feel free to ask me about this one. It's one that's really good to show you in detail. Okay, so we're looking at how many bonds there are. So I've got 1, 2, 3 NH bonds times by 4 is 12 lots of the 391. That's where this 12 lots of 391. And then we've got 3 lots of the double bond O's, 3 lots of 498. So you get a mark for putting 6186. That's the total amount of energy from the bonds broken. Okay, if we're looking at the bonds on this side, 2 of the nitrogen bonds is going to be 2 945s, and then we've got OH, we've got 2 of them here, we've got 6 lots of those 2, that's 12 of the 464, that's 7458 in total. Find the difference between those, and it's 1272. The reason it's got this little minus there is if you're doing it correctly, if you're getting it right, the overall change is a negative. It'd be 6,000 minus 7,000, so that's a difference of negative 1272. Okay, so you didn't gain or lose a mark for the negatives here. If you got these values wrong, you could still get a mark for subtracting your values and giving an answer. And for 5.6, this is where we were struggling. People found it very challenging, and not scoring is quite often because you just might have said it's exothermic or it lost energy to the surroundings. You need to put a reference into the bonds and the energies that you've been just been working on 5.5. Okay, so and it very explicitly says that. So the thing that we're looking for, saying, look over here at this first of all, right? That 7,000 energy released in making bonds is greater than the 6,000 used in making it. So more being made than is being used up. Okay, you could say that the overall energy change is minus 1272 because exothermic is a negative energy change. So although you didn't get credit for it in this question, if you did work out it was a negative change, you could use that in this question. The only way you get in this mark here about energy being released to the surroundings is if you get the first mark point. So if you just said it's exothermic because it lost energy to the surroundings, you aren't getting the mark unless you've actually used a numerical value like the question said. Okay, 5.7. Over here on the diagram is the same thing that was on the foundation tier. Okay, so common mistakes. If you did your arrow here, loads of people stopped it above the O2. You've not labelled the activation energy change. It should go from in line with the energy at the start all the way up to in line with the peak at the top. That's your activation energy labelled. You're not just drawing an arrow anywhere onto this shape. Okay, for the energy change, it should go from in line with the energy at the start down to the final energy. Okay. Energy change diagrams like that should be something that you're going into your revision, and it should be a nice easy thing for you to label. All right. This should look familiar to you if you looked at the foundation questions, because they had this exact same starting bit. So let's just say it quickly again. Temperature of the solution, the concentration of the electrolyte, or even the compound or ions or the type of electrolyte would be acceptable answers for this. You can't just say vague and not very specific terms like the electrolyte. You have to tell me what about it. Even even when you say something like the amount of solution is not all right. Okay, same thing, people also said the copper electrode. Okay, you can't just say something like that. It's a bit too vague. Okay, again, distance between the electrodes or the size of electrodes would have quantitative impacts on the end result. For 6.2, not everyone's getting the fourth mark on this one. Some people did, and I'm dead proud of that, so you did really good. Right, the order of reactivity. So magnesium, cobalt, nickel, tin. Most people got in the right order because you're going from biggest to smallest. If you lost a mark here, quite often people got copper and silver wrong because you said that copper must be the lowest because it got 0. Minus 0.46 is below 0. That's why silver's below it. So if your justification was that is the biggest number to the smallest number, there's where your 1 mark is, right? The proper answer is for all the positive values are because the metals are more reactive than copper. Apart from copper, obviously, which is the same reactivity as copper. The negative value, this is the 4th mark a lot of people missed out on, is because silver is less reactive than copper, obviously. Okay. Right, 6.3. Loads of people. Let's see what it nationally did with this. Yeah, half the people in the country are doing probably the same thing that about half of our class are doing, and ticking magnesium and cobalt. Now, if you look at magnesium and cobalt, the difference... Oh, I know why you're doing this. You're getting the 2 biggest numbers and adding them together, aren't you? Right, that explains a bit. Right, what you want is the biggest difference in reactivity. So it's magnesium and tin, because magnesium is a big number, and tin here is 0.48. So we're looking at the difference between those. There's quite a big gap in between those, 2.3-ish. Whereas if you compare like a really rubbish one like nickel and tin, nickel is 0.59 and tin is 0.48, so they've got a difference of about 0.11, so that's a really small difference. So it is about the difference in reactivity between them. 6.4, difficult question here, because most people are talking about things that aren't going to score them marks, so you think you've given a good answer. Steam trains release steam, water. So hydrogen fuel cells release water. That's the most obvious mark you can get. The second mark is for explaining where that comes from. So hydrogen and oxygen are combining together to release water. Okay, it's a bit of a pig of a question because it's a little bit simple compared to some of the questions that you were just doing. So I think it was pitched a bit wrong, really. Oh yes, more electrolysis. Don't we just love it? Didn't this just make your day when this came up? I mean, like, the good news is that this is probably not going to be something that's as detailed in next year's paper, but you will still probably have to think about electrolysis and reactivity. So why is a mixture used instead of only using the aluminium oxide? Very few people in our class remembered that cryolite is used because mixtures of materials change the melting and boiling points, so it'd have a lower melting and boiling point. Okay, so the reason we do that is because we then have less energy needed to heat this up, because it's going to be a lot to be able to melt this rock. How are we doing on that overall? 2/3 of people scored 0 marks on that, so don't be ashamed of that. But, like, you know, we have definitely done that in class, 100%. Okay, right. These weren't done well. So, aluminium is forming positive ions. It'd be Al3+ specifically. Specifically. So that would need to gain electrons to cancel those out. So that's the 3rd box down. Okay. Half equation. It's called a half equation because only half of the things are in it. So we're doing the oxygen half equation. So first up, don't write aluminium anywhere in it. Okay. 70% of people are getting 0 on this. So on the left hand side over here, we're looking at O2-. See that O2-? That's the oxygen ion. Okay, that is the anion. Okay, that is going towards the anode, where it can collect some electrons, which is going to where these electrons, these E minuses, come from. So ignoring the big numbers in front of it, if you got O2 minus and E minus in the right places, that could be where you got a mark for an unbalanced equation. Right, the reason I need two O2 minuses is because I'm going to make an O2 molecule. I need 2 oxygen atoms, and those would have 2 lots of -2, so that's 4 minuses, so I'd need 4 electrons to balance that out. Okay, you all need to go look at half equations. We all need to look at those. 7.4. Why the positive electrode must be continually replaced. Again, like this extraction of aluminium is important. It is in there. We spent an entire lesson looking at this. So forgetting about cryolite and forgetting this bit means that we've forgotten this lesson. We've not done the revision for it. Okay, we do need to look at that. Okay, so at the positive electrode, that's where, as a little bit of a clue, this was happening. What's getting produced? Oxygen's getting produced. Why is that a problem? Right, then first mark, that electrode is carbon. Okay, the carbon and the oxygen will react, mark, and produce carbon dioxide, the third mark. Look at all this like it's ignoring, like being worn away and corroded. Okay, 7.5. We wanted to calculate the mass. Right, so this was the first one, which is a bit of a pain for me to mark. When you're doing these calculations, give me an indication of what you're doing it. Whenever I'm setting these out on the board and like demonstrating them to you and getting them to write in the book, I'm asking you to write out formulas and label what you're doing and explain it. And when I come to mark it, I see numbers everywhere, and it can make it very hard for me to give you credit if you deserve it. Okay, now some of you might have been only 1 mark away from a grade boundary, and this could be where you might lose a mark, because if I'm getting paid like pennies to mark thousands of these and I'm just getting a snapshot of this, if I just see a mess of numbers and I don't see the right answer, 0 marks, move on. If you get it remarked, you might score some of these marks, but if it's not laid out in a nice way, you are possibly losing out on a bucket of marks here. Okay, let's have a look at how we're going to do it. So first thing, we've got our relative masses here, and we're looking at aluminium oxide, so we add them together. So we've got the 2 aluminiums and we've got the 3 oxygens, and if you looked at the foundations here, we already know that we added those up and we got 102. So if we want to work out how many moles, we will get the mass and divide it by the MR. That's our mass equals Mr. Moles formula. So we'd get 2 million grams, because that's 2,000 kilograms. Okay, and divide it by 102. That'd give you 19,608. Now, if you didn't turn it into grams, then you just miss out on 1 mark, because you get an answer that's slightly wrong. Okay, you get like 19.6. Right, the next step then would be to look at how many moles of oxygen that you'd make. So let's have a look at the ratio to them. So we've got 2 of these for every 3 of those. Okay, so when we times in 19,608, that's that number, by 3/2, we're just basically accounting for the ratio here. You're going to have half again as many of those as you will of these. Okay, so we have half as many again. If we call that 20, this is 30, so that's half again as more. Okay, so that's how many oxygen molecules we've got. And again, we go back to our mass equals Mr. Moles. We're going to get our 29412, and we're going to times it by 32. And if you notice, we've divided it by 1,000 because we're turning it back into kilograms. Okay, because the answer is in kilograms as well, which should give us 941. Okay, so if you left it all in kilograms all the way through, you can still get some credit through there too. Okay, right, 7.6. Oh, by the way, there is an alternative method there that you can use as well, a slightly different way of doing it. Absolutely fine. Because it's ratios, you can get it alternative ways. That's why it's really good to explain what you're doing. Okay. 7.6, why sodium chloride solution can't be used. Why to make sodium metal. So if it's a solution, it's dissolved in water. And then that introduces a choice. This one's a difficult one. These last couple of ones have been a bit of a pig, if I'm being honest. Don't worry about getting them wrong. Just try your best to get as many marks as you can from them. Okay, so if we had sodium chloride solution, sodium wouldn't be produced, hydrogen would come out of the electrode instead, and that's because sodium is higher in the reactivity series than hydrogen. For 7.7, here, the calculation one. So 150 kilograms of chlorine gas, so 1 mole is 24 decimeters cubed, so 2 moles would be 48. So okay, let's see how many moles there are in 150 kilograms. So again, we use our formula, mass equals Mr. moles, so we're going to rearrange that and get 150,000, because the kilograms, changing it into grams, come up again, and we're dividing it by 71, the MR. That means we've got 2,113 moles of chlorine. Okay, so if 1 mole is 24, 2 is 48, how much would 2,113 moles be? We're going to times them together. Okay? That should give us an answer of 50,700. And if you didn't change the kilograms to grams, then you're only getting one of the marks for 50.7. Okay, let's have a quick look through at question 8. Scary looking question, that, isn't it? One of the things then, it asks you straight away, why is step 8 needed? Step 8 is repeat this until the mass no longer changes. Why don't we want the mass to change anymore? That tells us the reaction's finished. Okay. It also means that there's not any other contaminants like the water that's produced. So that's I don't think I saw anyone mentioning that. 8.2, not as well answered. How well was that answered overall? 8.2, 80% of people scored 0. Yeah, that's not surprising, is it? The first mark is for saying that you want to make sure that the hydrogen is not escaping into the air, otherwise you will slowly fill the room with hydrogen. Why would that be bad? Squeaky pop, but that would be a squeaky pop the size of a room. Okay, so because hydrogen is explosive. Most people are getting it wrong because you're saying that hydrogen would interfere with the mass of the solid, which it wouldn't, because it's got a hole on it. It would be free to leave the container. Okay. I was surprised that only a third of people got this next mark correct. They're the numbers we're going to be referring to in a second. So there's a lot of numbers here that could have confused us when we're trying to work out the copper produced. The empty tube is 105.72 grams. The tube at the end with the copper in it is 114.38. So therefore the difference between those, 8.66, is how much copper has been produced. Okay, slightly easier. I'm going to say slightly easier, a lot easier. If you look at tube B where the water is being collected, find the difference between these two bits. It's increased by 2.45 grams. That's where that mass has gone to. Okay. So that was 8.3. 8.4. We're looking at which one of these is correct. So the way that we could look at it is, if we work out, if we've got 2.54 grams of copper, we could work out how many moles there are of it. Okay, so we get our mass and we divide it by our MR of 63.5. That means it's 0.04 moles. Okay, now if we're looking at equation 1, there should be twice as much copper as there would be for the water. And if we're looking at equation 2, there'd be the same amount. So let's do the same thing with the water. We get our 0.72 grams, our mass of 0.72. We divide it by the MR, 18, and we get 0.04 moles. That's the same. That means it must be this one here, equation 2, with the 1-to-1 ratio. Okay. But again, because it's a question about ratios, there's other ways of reaching that same final answer. Make sure that you're nice and clear and signpost what you're doing. Don't just put numbers everywhere and confuse the poor person marking your results. Question 9.1 then. Most of the wrong answers in this case here, people are talking about safety features. Okay, if we're talking about energy changes and temperature, it's about insulation. Okay, so we already mentioned this when we talked about the foundation. If instead of using a glass one, we can use a polystyrene cup, not because it won't react, not because it won't shatter, it will insulate it more and prevent heat loss. 9.2, right, most people got 2 marks at plotting the points on the graph. A line of best fit was then drawn, which usually got you the 3rd mark. The bit which most people lost marks on was they extended both of these beyond where they met, so you had them sticking up at the end still past. Now a line of best fit should follow the pattern, so I'd expect to see that it got hotter, it got hotter, it got hotter, it reached a peak, and then it started going down again. It can't be going up and down at the same time. So some of the stuff that you're drawing on the graph, though I've circled it, extended too far. Extend until they cross, but not until they go past each other. Still not sure if I've been too harsh on that by not giving you the mark or not, but I'll chase that one up. On 9.3, it says use figure 11 to determine the volume of dilute sulfuric acid needed to complete reacts. So for that one there, we're using your graph. So we go across to where it reached its peak, and then we go down, and it should have been somewhere around about here, which should be something about 11. Okay, a little bit of tolerance depending where you made those lines cross over each other. For 9.4, where it's asking you for the overall temperature change, we're going to look at the highest temperature, which should be around about 27.5, somewhere about here. And then the lowest temperature, so then that came down over here, it met at 18.9. And then find the difference between the two, which should be 8.6. Okay. When we're on question 9.5, this is the joyous end. It's clearly meant to try and stretch people, this one. Let's see how many people actually got this right last year. A third of students got absolutely nothing right on this one. So, you know, a lot of people doing the actual GCSEs got this wrong. So let's have a look. It's a titration. We know we've got 15 centimeters cubed of the 0.5 mole sulfuric acid. The first thing that I know that we can do there, change that into decimeters cubed, and then we can start finding out how many moles are there. Okay, so that's what we're doing here. That divide by 1,000 over there is to turn it to decimeters cubed. We're doing our concentration is the number of moles divided by the volume formula to get this arrangement over here, and we can work out our number of moles by timesing the concentration by the volume, and that gives us 0.00775 moles. And that was of the sulfuric acid. So the sulfuric acid here, okay, I've got a little invisible one in front of it here. There's twice as many potassium hydroxides. So we're going to double it. We're going to get that 0.00775. We're going to double it, and it's 0.0115 of the potassium hydroxide. Look how this is being set out each time. It's telling us what we're doing. So if we're looking for the marks, that's where we're getting it from. Okay, now we've got a number of moles. We do have a volume here, so we can do the number of moles divided by the volume, which would give us our concentration, 0.62 moles per decimeter cubed. Super exciting stuff, isn't it? Alright, here's where you could get at least one of your marks. When we're looking at trying to do the concentration in grams, we need the MR, so you're going to get a mark for adding up the K, the O and the H and getting 56. So the concentration in grams, we need to work out the grams, so the mass. So mass is Mr. moles, we can get that 56, times it by the number of moles that we know is there, and that would give us the same answer through what they're working through here as well. Okay. There were a couple of alternatives way to do it. I saw at least one person doing it through this way, and again because it's all ratios, you can get to that point. You can get that the same way too. Okay. Well done for making it this far through. Do have a look through for the bits that you struggled at. Ask me if there's any bits that need further explanations. If you're on the iPads, make sure that you use Seneca or something like that so that you can target some of these areas, and then we can keep making those little improvements, get you the extra marks to get you up to that next grade boundary. Remember, you know, top end grades here are like 60% territory, 70% territory. So you only need to be getting half the marks. Even on this last question at the end, you only need to be getting a few of the marks, and you're doing the right job.